I really need to study for my feedback test, but I also need to drive to the test. I wish I had a PI controller to do this for me. Good thing I know how to build a closed loop feedback system that's BIBO stable.
The current feedback controls found in most cars today lack the capability to autonomously accelerate and decelerate in a way that requires almost no input from the driver. An autonomous car would require multiple feedback systems for different variables such as acceleration, velocity, and position. We will be focusing on the velocity aspect of a car accelerating from 0 to 60 miles per hour to replicate the transition onto a highway. So we simplified our driverless car model into a mass damper system, which you can see here. It's got the mass of our plant, which is a 2016 Prius, and that has a mass of 1,325 kilograms. And then we've got a damper, which comes from the friction between the tires of the car and the road, which we calculated using this equation to be 66.25 Newton seconds per meter. And then we've got the input from the engine as the force. So we converted our mass damper system into an impedance diagram, which you can see here. And the impedance of a mass is 1 over ms squared, and the impedance of the damper is 1 over bs. So from this diagram, we solve for the transfer function, which is this x of s over f of s, and that was 1 over ms squared plus bs. And then that's the position transfer function. So we took the derivative of that to get the velocity transfer function, which is 1 over ms plus b. And that is the transfer function that we're going to use in our final feedback system.
This is our open loop feedback system, and as you can see, we have 0 zeros, and our poles are at negative b over m, which gives us a value of negative 0.05. Under further analysis of our transfer function's response to the step input using our actual mass and damping values, we can get a k value of about 0.015 and a sigma value of 0.05, which can then be used into evaluation of our rise time and settling time that Jordan will further explain.
Thanks, Peyton. So from Peyton's analysis, we were able to develop a root locus plot. From here, you can tell that we only have one pole and no zeros. And this pole shows that our system is BIBO stable because it has only real negative parts at negative 0.05. From this analysis, we were also able to determine our rise time to be roughly 43.9 seconds and our settling time to be about 78.2 seconds. For real world applications, these aren't great times because say you want to merge onto the highway, it would take you roughly a minute just to get up to 60 miles per hour, which isn't really safe when you're trying to merge into traffic. And also there's going to be other factors that we'll have to take into account, such as air resistance and if the road is on an incline, so this will also then affect our rise time and settling times. But you also can tell from this plot that our one pole does approach infinity as we move towards stability, and so from here we can tell that this isn't the kind of system that we'd want to use in a real world because it would take too long, but if we were to include a PI controller, it might change things.
So this is a Simulink block diagram that we created for an open loop feedback system. And using this, we got a step response graph, which has a rise time of about 43 seconds, which is the amount of time it takes to get from 10% to 90% of the final value. And then it has a settling time of 78 or 80 seconds, which is the time it takes to get to the final value. And because of this, those are pretty high values. So we decided to add a PI controller.
After analyzing our open loop response to the step input, we decided on 3 design specifications that we'd like to include in our new feedback system. The first design specification would be a rise time of less than 9 seconds. Right now, the Prius already in the real world accelerates from 0 to 60 miles per hour in 9.6 seconds. So with that being said, we want a final value to be 60 miles per hour, which gives us a steady state error of at least less than 2%. And our third design specification would be a less than 10%
This is
overshoot.
a Simulink block diagram of the feedback system after we added a PI controller. So all of this, it's the same as the open loop feedback system. It's inside this plant model right here, and the PI controller is right before it. And we had to choose KP and KI values for the PI controller. And from the design specifications that Peyton just talked about, we decided to go with 600 for KP, which is gonna decrease the rise time. And then we went with 30 for KI, and that's gonna eliminate the steady state error. So from this, we generated a step response graph that shows a settling time of about 8.7 seconds and a rise time of 4.3 seconds. So that is within our design specifications.
Okay, in further analysis of the step response that Matt just brought up, we can see that our final steady state value is 60 miles per hour, and it stays at 60 miles per hour, which is exactly what we want and gives us an accurate final value as well as a steady state error of less than 2%. And with even further analysis, we can see that our rise time is actually 4.85 seconds and a settling time of 8.63 seconds, which is less than our design specification of 9 seconds. Also, you can see that our overshoot is 0%, which also meets our under 10% specification.
Alright, so without the PI controller, we were able to generate a bode plot, and as you can see here, we were able to determine that our phase margin is going to be infinite, which is basically the opposite of what we want, because that's going to mean that we're going to have excessive error when we are testing difference reference signals, which could be incredibly dangerous since this is going to be interacting with human lives, and they could cause crashes if there is excessive error. So after adding the PI controller, we were able to generate a new root locus plot, which shows that our system is still BIBO stable. We no longer have a pole at negative 0.05, it's now at negative 0.45, and it has only real negative parts, so again, it is BIBO stable, and it does still tend towards infinity. And based off the information from the root locus plot, we were able to generate new bode plots with our PI control. And from here, by adding in the PI control, we no longer have an infinite phase margin. We now have a phase margin of roughly 95 degrees, which is still out of the range that we want, because 60 degrees is the closest to stable that we would like to get. We tested a lot of different gains to see if we could get it down to 60 degrees. Unfortunately, we couldn't, and we determined that the only way to get it to that range would be to add in a new pure integrator into the feedback system, or to add in a lag compensator. In conclusion, this is just one way that feedback control systems can provide a solution to everyday technological problems and provide a better future for humans.